All right, so today we are going to be talking about planetary geology, mostly the beginning about this. We're going to go through kind of how the terrestrial planets in general formed, how they're shaped the way they are, what's important about them, why the surfaces look the way they do. And then if you haven't been here before, what we do is this lecture takes about, this will probably be about half an hour, and then we'll kind of just do an AMA for the rest of the hour if we want to talk about any sort of random astronomy questions that we have or anything that's been happening lately. And if I don't know the answer, we'll look it up and I'll at least interpret the results for you, because I have no shame in saying I don't know. But yeah, what we're going to do today is just go through some of this planetary geology in general, and then we'll talk about specific planets next week. And if you're watching this live, you can stay here for the AMA. If you are watching this after the fact on YouTube, then catch us live next time so you can take part. All right. So let's kick things off. So last week, not really last week, the week before, because I had to take a week off, we talked about the formation of the solar system. And actually, if you follow me on Twitter, or yeah, if you follow me on Twitter, I just retweeted someone who had a great breakdown of this as well. But basically talking about how our solar system formed from a cloud of dust and gas. And as it started to form, we got these, you know, these gravitational impacts that are happening. You start to get these little dust particles that kind of coalesce, run into each other, get a little bit bigger, increase their gravity, so more stuff crashes into them, and you get this like snowball effect. And in the middle, you get this really sort of hot, it starts to heat up because of friction, and it starts to get really dense. And then once that has reached this sort of critical temperature density, it starts fusing the hydrogen gas into helium, and then at that point we have a star. However, as that's been going on, all of that dust and gas has started to kind of coalesce and shrink down through gravity and angular momentum and these random processes that averages out to be a flat disk. And then we get these planetesimals, and those planetesimals start to clear out their orbit, and we'll go through today how we get these terrestrial planets. So when we talk about the age of our solar system, remember we're saying that our solar system is about 4 billion years old. One of the things we can do is try to determine through the age of rocks. Now, if we're pulling out an individual atom, whether that's hydrogen, carbon, nitrogen, anything, you can't just look at a single atom and determine how long it's been around, how long it formed. However, that if you have a solid structure that's made up of atoms, then those will start to undergo changes that determine how long it's been held in place in that solid structure. So what we're really doing is we're finding the age since the rock has solidified. Hey, Atma. How we go through this is actually called radiometric dating. And we talked about this a little bit, I think actually in our episode club when we were talking about how in Star Trek Next Generation, All Good Things, they could tell the proportion of air molecules that were in Picard's lungs to determine that he hadn't been off of the ship, and then figuring out how much time had passed based on that. So it was pretty intense. Hey, Trek Nerd. I'm glad. So this radiometric dating, basically what we're doing is we're measuring the rock's proportions of different atoms and isotopes, what we have. So remember, isotopes are when you take an atom, atoms are made up of protons and neutrons, and then they're orbited by electrons. The amount of protons that are in the atom determine what element it is. So, you know, 2 protons is a helium atom. And then we have 6 protons. That's usually the best one. 6 protons is a carbon atom. Hey, Shortman. And typically, you'll have an equal amount of protons and neutrons, but sometimes the amount of neutrons can change. So if you've heard the term carbon-14, what that means is you have 6 protons and 8 neutrons, and those are what we call isotopes. So if you can measure the proportions of different isotopes, that can help us do radiometric dating. And the reason that it's good for this is because some isotopes are radioactive. And when we say something is radioactive, what we're really saying is that that nucleus, that the protons and neutrons, undergo spontaneous change. They'll spit out protons or neutrons, and then they'll change themselves. And this transformation that happens overall happens at a steady rate. And so the way that we measure this is something called the half-life. So you have this, set of isotopes, and those isotopes over time are going to go through these random changes. But that random change, when you're talking about, thousands, or if you remember things like a mole's worth, Avogadro's number, anything like that, overall, that will follow a steady process, which is what you see here. And then we determine the half-life is the time it takes for half of that parent nuclei, that isotope that you're starting with, to decay. So it's half of it has disappeared and it's changed into something else. Hey, Becca. Oh, good to know. Thank you for the recommendation. So uranium-235, that's basically saying its weight is 235. And remember, that's the combination of protons and neutrons that are in there. Hey, Planetary. And what that does is it actually, it decays, and then that's half-life of uranium-235 is 704 years. Yay! And these rocks can contain more than one radioactive isotope. So that's really helpful, because sometimes it might not be, a whole lot of material. You're not getting, because you want to get this average, you want it to average out so you're able to get a good read on how old it is. But rocks will contain more than one radioactive isotope, so you can compare them all. Knowing the half-life of these individual isotopes can help you determine kind of what your baseline start was and how old the rock is. Now, when we talk about planetary geology, the term planetary geology, geology officially, geo, means Earth, the study of Earth. So when we say planetary geology, it's kind of like an ATM. It's not even an ATM machine. It's the opposite of that. That it's exactly not of what you're talking about. But it's just the extension of geology to other worlds. Yeah, oxymoron. That's the correct one. Thank you. So because we remember our solar system is broken down into 4 terrestrial planets and 4 jovial planets. Jovial. It's been a week. Jovian planets. I suppose they're happy. Jovian planets. And then we have our dwarf planets, our asteroids, all of those other things. But if we're talking about our terrestrial worlds, we have Mercury, Venus, Earth, and Mars. And then we kind of throw the moon in there too, just because, remember, the moon is one of these outliers in finding patterns in our solar system. For the terrestrial planets, it's incredibly large. It's a large moon in proportion to the other, to its parent planet, us. Mars also has moons, but they're like small potato-shaped moons. So the moon is an outlier. We can kind of call it a planetoid, planet-like. And yeah, and we can study that as well. So what we've been able to learn through various studies, whether we're doing sort of radar studies or measuring sort of the magnetic field or building computer models to see how we can get this stuff out. Yeah, we can start to build up what's on the inside of this. So we have these 3 major components that are the crust, the mantle, and the core. And if you remember from school, the crust, that's that really thin outside. That's the skin layer. Then you have this mantle. That's going to be a good chunk of it, the majority of it. And then we have a core in the middle. Now, Earth has a solid and a liquid inner core here. And then looking at the other planets, particularly with Mars, that changes how we can determine what type of interior it is. Hi, Uncle Bill. All right. So what planets are like on the inside, it really layers out by density. Oh, and thank you for the host. This core, like I said, that's the highest density material. That's in the core. It's primarily made up of metals like nickel and iron. Then outside of that, the majority of a planet here, we have the mantle. Now, this is the rocky material. It's moderate density, and it's going to be more minerals that are like silicon or oxygen, and that's going to be a big part of that too. Oh, thank you for the follow. And then, like I said, the crust is this really thin outer skin, and it's the lowest density, like made up of granite and basalt. And how this sort of shakes out, it's really important to note. And it's one of these things that maybe if you haven't thought about this, you're realizing it for the first time, and that's okay too. But remember, I'm saying layering by density, and the way things that can differentiate, I'm trying to use the word without actually saying differentiate. The way things separate by density is called differentiation. I'm sorry to hear that, Big Fun Art. I will dig into that a little bit to see if I can help with that at all. It may be something on my end. There's still some nuances that I try to figure out, but I've definitely heard that before. I also have a Discord channel, but that usually takes about 5 to 10 minutes for that notification to go live. Anyway, all right. So differentiation. That's where think about it this way. If you've played with the oil and water, right? You shake up oil and water, or vinegar and oil if you're making salad dressing, something like that. If you shake it up and then let it sit, what it's happening is it's differentiating, and it's basically separating by density. And so that's how we end up with the core, the highest density, then the mantle, medium density, and then the crust is the thin layer. And then we also have differentiation in the atmosphere as well. Note that it's not to scale. And all of that differentiation as a planet is forming actually dictates how the interior layers of a planet get hot. And yeah, Becca, that's a really good point too, that when you're talking about sedimentary rocks and the layers there, that's essentially what's going on, because sedimentary rock, that's the layered rock, and then it's just and then what it's doing is it's settling out the heavier material, the rocks, in this liquid. So typically a lake or an ocean or something, the rock layers will settle down, and then the geological processes happen, more rocks are introduced, and then they layer down again. And so you get these layers of rock as you go, and that's how you get sedimentary rock. And we're going to talk about that a little bit here as well. But the ongoing changes that are inside of a planet include accretion, differentiation, and radioactive decay all contribute to a hot interior on a planet. Billy. All I saw was episode club and the core, and wondering if, like, yeah, people were like, yeah, that's... So the core. Let's save that for the AMA at the end. Where we can talk about, because I'm gonna need some reminding. It's basically the core stopped, and then they tried to bury a nuke, right, to restart the core. Yeah, we'll talk about that at the end. But be prepared to remind me exactly what the plot was, because it's been a long time and that movie stressed me out. Yeah. Okay, so accretion. That's kind of what's being demonstrated here. We have stuff that's crashing into the planet, so it's building up the planet. But remember, when we learned about energy, conservation of energy, and energy transfer, what we have is when something crashes into a planet, that is coming in, and it has kinetic energy because it has a speed, and once it crashes, though, that kinetic energy has to go somewhere. And now that can be transferred because we have kind of a collision that's happening. So if it's really big, you can think of transfer of momentum. So that mass and the velocity is now, a non-elastic collision, that it's gone and it's attached. But also you can lose energy from thermal energy. So when it crashes, it's going to transfer some of that energy to heat. That heat is going to contribute to a hot interior. And this is particularly important when we're talking about the early formation of planets. Because remember, there's that whole period where it's all kind of shaking out and lots of chaotic processes are happening. Lots of things are running into each other. And even as these planetoids are starting to clear out their orbit, they're still running into a lot of stuff. So it's this accretion. That's what's going to be building up a lot of heat on the planet itself. Differentiation is going to be a major part of this heating of the interior. So again, when you think about the early formation of the planet, we just have a lot of hot crap that's all kind of coalesced with itself, and it's all starting to come together. Oh, thank you, Lake Girl, yay! It's all kind of come together, but it hasn't settled out yet. So we have different minerals. Remember when I was talking about how the mantle and the core and the crust are all made up of different minerals, atoms, all of those things. Those are all just mixed together in one big thing. This is like when you've just shaken up your salad dressing, right? And then you let it sit. that sitting process, once it's cleared out its orbit, it's got a lot of accretion, it's kind of built itself up, then that differentiation is starting to take place. And so now we're starting to get things to settle out. And as it's transferring, where you can see here this hot, the heavy gray stuff is going to the middle, the lighter stuff is moving to the outside. As it's moving, we're having friction, that's going on. And so that's contributing to some heat as well. And then the material themselves is undergoing radioactive decay, just because they'll be made up of unstable isotopes, and some of them have incredibly long half-lives. So the idea that you could have uranium-235, for example, be a part of this and undergoing decay, that contributes to the heat as well, because when it decays, it gives off some energy. Okay, so now we have our planet. We have a hot interior, we have a crust, it's all kind of settled out. We have our layers, we have our core, our mantle, and our crust. Then it's basically going to start cooling off. And how that cools off is once these layers have all kind of settled out, we get this convection, conduction, and radiation. And I want to make sure I say this right because I never say it right. And I'm okay with that. So convection is where you get the hot material expanding and rising up, and then cooling off and following back down. So it's bringing heat up, and then it loses that heat and it goes back down. Convection ovens. Yes, the denser things are in the center. Did I say that backwards, Trek Nerd? Thank you for catching that. It should be. That's what it should be. If I didn't say that, then that was wrong. So I apologize for that. But thank you for catching that. And then conduction. Okay, so convection, think about convection ovens, right? The hot air rises, cools, falls again. And then that's the convection process. And that cools off because there's little, it's not totally gone, but there's little sources of heat left now. Really just that radioactive decay that's going on. And so that radioactive decay is causing some heat to happen, but we have a hotter core. And so as this goes up, it starts to cool off, and then it falls back down again. And then it still heats up because the hot is still, or the center is still warmer. So it heats up and it rises again. And then conduction is that process of as that material is rising, it's cooling off because it's hot and it's meeting colder things, and there's a heat transfer process that happens. That's conduction. And then radiation is the heat actually leaving the planet itself. That's where it's radiating off. It's where we talked about that black body radiation, the thermal curve that we get. That's how all of these processes start to slowly cool off the planet. Okay, then we talk a little bit about the magnetic fields, and this is kind of where the core comes into play here. But we have this interior region, and it's going to be high metals, right? Because this is the most dense, is going to be at the center. And then we have that inner core, the outer core, we have the inner mantle and the outer mantle, and we're going down in temperature as we're going out. We're going least density as we're going out. But near that center part, particularly if we have this outer core that's liquid, that's going to be rotating, and the convection that's going on. So we have electrically conducting fluid. We essentially have metals here that are able to conduct electricity. We have convection that's going on where the heat's rising and then it's falling again, all in this core here, this liquid outer core. Because it's going through that process, it's basically generating an electromagnetic field that then propagates through, because there's kind of nothing to stop that. That's where the core itself, the fact that it's metal, that's the magnetic part that creates this magnetic fields throughout the planet. So I hope that makes sense. I know I kind of burned through that a little bit. Let me just make sure I didn't miss any of the main points here. So I guess it's important to note that if you don't have this electrically conducting fluid, a liquid part of your core, that's the main component, because you have to have a dynamic process happening in order to generate a magnetic field. And so if you don't have that, you're not going to get this magnetic field. You need to have convection in that layer of fluid, so it can't all be one temperature. You have to have it hotter toward the center, cooler toward the top, such that, to drive that process. So it has to be liquid so it can actually move. Then there has to be a temperature differential so it can actually go through a convection process. And it has to be moderately rotating, which can also drive some of those dynamic changes. And not protected from the sun, right? So when you have this liquid outer core, the fact that you have temperature differentials, the planet is rotating, and that it's liquid itself, all of that is what contributes to generating a magnetic field around or in the planet. So that's how we get the center of planets, and how we have some planets have magnetic fields, some planets don't have magnetic fields. Now, we'll get into each one individually. We'll talk about Earth versus Mars. I know I've touched on Mars quite a few times here, but it's really important once we get down to that specifically, and we'll learn individually about each planet, talking about why Mercury's core is the way it is, why Venus is the way it is, why Earth and Mars are the way they are, and some of the different theories about them. So let's move out. Now we've got how we got the core, how it heated up, how it's cooling off. We'll talk a little bit about moons today. We're not going to be touching on the Jovian moons right now. But yeah, not today. We'll get into the specific bodies next week. Not sure if we'll fit in Europa next week, but that's just the one I'm most excited to talk about because it's amazing. But first we want to talk about just in general how these surfaces of these planetary bodies look the way that they do. And there's four main components that contribute to the surface of these planetary surfaces. First is impact cratering. So this is the, stuff crashes into it. We get an asteroid impact. Oh, yeah, fair enough. And Ganymede as well. Yeah, that's fair. We also have volcanism. So volcanism is this eruption of molten rock or lava from the interior onto the surface. That kind of, it's again one of those things where we talk about volcanoes. Everyone's like, yeah, okay, I understand what a volcano is, but it's thinking about it from a definition standpoint and understanding what processes are going on to that. So that's where we have this liquid material underneath the surface that is then being sent up to the top through a volcano. Then we have tectonics. So that's where you have internal stresses on a planet, on the crust, are going to cause that crust to move and shift and go through tectonics. And then erosion. So this could be things, this is, atmosphere, water, any of that stuff. It's just the wearing down or building up through wind, water, ice, and any other sort of planetary weather that we have here. So let's talk about impact cratering. Now, this is primarily seen not necessarily on Earth or Venus, though, as you can see here, it's not exclusive, because we go through erosion, but impact cratering is very much seen on the Moon and Mercury. And that's just because they've taken beatings from comets, asteroids, all of this stuff. And because they don't have a atmosphere, those don't go away. The other important thing about impact craters is that small craters outnumber the large ones, which helps us start to understand how many small objects versus big objects, what the distribution of objects is in our solar system. Because remember, asteroids are actually really, really, really hard to see. They're incredibly dark, incredibly cold, so they're not going to be giving off a lot of heat. They're not giving off radiation. They're also dark, so they're not reflecting sunlight in the same way that like ices are. So they're really hard to see. But if we can look at the impact craters on the Moon or Mercury, where there's not an atmosphere, and as far as we can tell, there hasn't ever really been one, we can start to understand the history of our own solar system here. Now, craters are usually circular, usually because this impact blasts out everything in all directions. You can do these tests. I mean, it sounds kind of goofy because you see kids doing this at science museums, but it is legitimate research where you barrage a surface of, maybe flour or something and drop a marble into it and see how the distribution of material goes out. So understanding how many times you're going to get a circular impact crater versus maybe one that isn't circular, that is something that has been studied, and we find that that they're circular. Going through different other experiments, we can learn that craters are typically about 10 times as wide as the objects that create them. So if you see one, divide it by 10, and you can estimate about how big the thing was that ran into it. And about 10 to 20% deep as they are wide. So just if you can only look top down and you don't have the depth perception for, you know, whatever reason, you can estimate about 10 to 20% deeper than it is wide. And so, for example, an asteroid about 1 kilometer in diameter will blast a crater about 10 kilometers wide and about 1 to 2 kilometers deep. So those sort of, you know, tests you can do on this to try to figure that out. Oh, thanks, Vicar. We also get clues about the geological conditions from impact craters and looking at crater shapes. So you can tell, for example, if you have like a bump in the bottom of it. So some of you have seen those. I'm sorry, I don't have a picture of them actually. But if you have a bump in it, that can indicate that, you know, maybe that there is a little bit more viscosity, a little bit more water, liquid, ice, something like that, that could contribute to this bump popping up. So there's all these different things here. How much do atmospheres affect that ratio? That's a really good question. So that initial impact crater is just going to be what specifically hit that. So that's not saying that essentially or effectively, let's say, for example, we take a 5 kilometer wide asteroid. By the time it gets to the surface, if there's an atmosphere, it will have eroded away the size of that asteroid. So maybe it started at 5, now it's only 1 kilometer. What we care about for the crater impact is just the size of it when it hits the ground. So it will lose matter, it will lose size by going through the atmosphere. So looking at impact craters on the surfaces of planets that have atmospheres are not necessarily going to tell us how big the asteroid was when it came through, just how big it was when it hit. We have to understand, and that's for studying other planets, we have to understand the distribution of the atmosphere, how dense it is, all of those things. Now on Earth, we can do that, right? We understand our atmosphere, so we can say, okay, we saw, you know, the impact crater that killed the dinosaurs, for example. If that was X big and it went through our atmosphere, then it would have eroded this much. So that's how big it was before it came through the atmosphere. So yeah, all of the sizes that I was talking about are just whatever object made it through the atmosphere to impact the surface. That's where that came from. And then Andy asked how strongly the density affects these rough estimates. Really good question. So because we get this differentiation with the material that forms a planet, we have a good sense for that crust density because that's going to be the lightest rocky stuff that is present in our solar system that made up the planets. So for example, on the surface, and again, I have to check this up, like granite and basalt. Now, the amount of granite and basalt on the crust is going to be slightly different. But for example, we're not going to necessarily get a metal crust on the surface. So when we're just talking about these rough estimates for impact craters, we're thinking light, rocky material in general. And in that sense, those rough estimates hold up. Again, it's about 10%, 10 to 20%. They're rough estimates. But for the most part, because these very outer crusts are made up of a fairly similar material, it doesn't impact that much. What does impact, and that's kind of what I was trying to get to a little bit, is that the density affects the details of the shape of the impact crater. So you have that typical bowl shape versus a bowl shape with like a little bulge in the middle of it. That's going to more dictate the density of what it crashed into. Makes sense. Hope that makes sense. Okay, cool. Awesome. All right, so then we get volcanism. So let's go into that. Volcanism. So we talking C, S, and M type asteroids, not including a rubble pile. We're talking about different density for asteroids. Oh, that's a good question. So I was referring to the density of the crust, not the density of the asteroid itself. If that's what the question is, that's a little bit different. That's a good point. But yeah, let's look up those different, because I don't have those off the top of my head, what those are made out of individually, how the density of the asteroid affects it. I think the density of the asteroid affects more how, let's think about that for a second. The density of the asteroid affects more how much it's going to erode in the atmosphere versus what type of impact crater it's going to make. And I say that because if you're going to do a science experiment where we have a, tub of flour, and I drop a ball bearing versus a marble, they're still going to fall at the same rate. They are still going to make a circular impact crater. I really want to do a science experiment. And I don't have the stuff for it. But anyway, we'll dig into that a little bit more once we get through this. But thank you. That's a good question. All right, so volcanism. This is any type of molten lava, whether it's a, tall volcano or it's just risen up through the cracks. Volcanism occurs when you have an underground path to magma makes its way up to the surface. So molten rock tends to rise for three main reasons. We have molten rock is usually less dense than solid rock, and so it's kind of differentiates itself. Because most of Earth's interior is not molten, the solid rock surrounding a chamber of molten rock can squeeze that stuff, driving it upwards. And then the third thing is the molten rock often contains trapped gases which expand as it rises because there's less pressure holding on. So as it rises, those bubbles expand, which is going to drive it further up as well. And that's how you get these dramatic eruptions that comes up. The result of these eruptions depends on how easily the lava flows on the surface. So, where you're thinking about, these examples where it's really runny, really hot, it's going to flow a lot faster versus thick lava is just more going to pool in one spot. So these runniest lava flows, the runniest lava flows really far and flattens out before solidifying. That's how you get those plains. And then thicker lavas solidify before they spread out. That's where you get those like shield volcanoes, which can be very tall but not very steep. So things like the Hawaiian Islands, for example, are these shield volcanoes. And then the thickest lavas can't flow very far before solidifying and build up tall, steep, what we call stratovolcanoes. And that's going to be like Mount Hood or Mount Fuji. I think that works. Cool beans. So it's typically made up of basalt is what this lava rock are made out of. And yeah, let me see if there's any other details. Like I said, this is Astronomy 101. It's not necessarily a geology course, so we don't have to get to all the details of volcanoes. But understanding what forms volcanoes and why different volcanoes look the way they do here on Earth helps us understand other planets, particularly when we talk about like Olympus Mons. So that Olympus Mons is very much a shield volcano, and it's technically the tallest volcano in our solar system that we've been able to see. But it's the shield volcano. It's very tall, but it's not steep. And that tells us a lot. It tells us about the consistency of the lava that formed Olympus Mons, which is pretty cool. Pretty interesting to think about. All right, and then we get tectonics. So tectonics here, we talk about that, particularly with Earth, I think we understand them pretty well, that how we get the different plates and how they move against each other, where you get that, I'm not a geologist, you can tell. You get the plates that go under the other plates. You get the plates that shift against each other. But all of those are being caused by these stressors that are inside of the planet's interior. And then these plate tectonics, subduction. Subconduction? Subduction. It's just subduction plates, I think. We'll get there. I learned enough to know why I have earthquakes here in LA, and I learned enough to know why the Rocky Mountains formed in Colorado, where I grew up. And that's the only stuff that's stuck. But It still is important, though, because if we're able to see tectonics or evidence of tectonics on other planets, that also can tell us a little bit about the history of the core, because it tells us how much stressors, how much pressure was put on the surface of the planet. If we have these plates, if we see past cracks, if we see mountain ranges that look like they were formed, that tells us something about what the interior looked like, that it was liquid, that it did have stressors and different pain points that are on the surface here. No worries, Cairo. Happy to have you here. And yeah, I'm glad you caught part of this live. No worries at all. All right, and then erosion. So erosion is kind of the to planetary geology, because it erases the history of the stuff that's happened there. Thank you, Brad. Exactly. Situational, functional earth science knowledge. That's the extent of my geology. I know enough to be slightly dangerous, but only slightly. All right, so erosion is that breakdown or transport of surface rocks through ice, liquid, gas. So shaping valleys, shifting sand, all of those. And then as Becca pointed out, this is also how we get sedimentary rock, that it deposits layers as we go. Really cool, interesting stuff. And, you know, is important when it comes to also understanding the history, even though it's a little bit annoying when we're talking about the fact that, you know, Mars may have had there's evidence that Mars had an atmosphere at one point, so that means that it did undergo erosion. So when we're seeing the surface, we're not seeing it as it was when it first formed, as opposed to when we're looking at Mercury or the moon. However, seeing what erosion we can identify on Mars also tells us something about its past. For example, we have the big crack, Mariner Valley, on Mars. We can look at that, and understanding our processes of erosion here on Earth that formed things like the Grand Canyon, we can look at Mariner Valley and determine that erosion did not cause that valley in the same way that the Grand Canyon formed here. So it can be used for good and for evil. To learn things and to rule out things. So it's still an important component that doesn't make us just want to walk away and cry, but we can actually determine some of the past history here that's going on. Okay, so that's it for this week's set. Now, like I said, for the people who are here live, we're going to stick around until the top of the hour and just kind of do an AMA. And obviously from the questions here, we're definitely going to talk about the core, the movie. But if you're watching this after the fact on YouTube, we are going to be ending it here. So please feel free to leave comments and questions down below. Like, subscribe, do all of that fun stuff. And if you can catch us live at 1 p.m. on Fridays, 1 p.m. Pacific time on Fridays on Twitch, the link is down below for that too. So for those people, thank you for being here, and we'll catch you next time.